Listen. Even churchies need to have beers. Okay, so we're on page 64 and 65, still on section 1, Theory of Heat. Unit 3, Refrigeration and Refrigerants. I'm only having one, by the way. But this is not, and I'm highlighting. Decided I'm going to highlight. It's my book. I can mark it up as much as I want. But this is not absolutely accurate because it refers to the heat content above the selected reference point. Refer back to figure 1.14. Oh, that's way back there. This is going to take a second to find figure 1.114. Oh, and I keep ripping my book. Okay, so that's just the heat/temperature graph for 1 pound of water at atmospheric pressure. Explains how water responds to heat. An increase in sensible heat causes a rise in temperature. An increase in latent heat causes a change of state. For example, from solid ice to liquid water. So, the heat/temperature graph for water. We use 0 degrees Fahrenheit as the starting point of heat for water, knowing that you can really remove more heat from water, ice, and lower the temperature below 0 degrees Fahrenheit. We describe the process as the amount of heat added starting at 0 degrees Fahrenheit. This heat is called enthalpy. Highlight. The pressure/enthalpy diagram is a similar diagram, available for all refrigerants and sometimes referred to as a PE, pressure/enthalpy, or pH, pressure/heat chart. Since different refrigerants have different characteristics, properties, and temperature/pressure relationships, the pressure/enthalpy chart for each refrigerant is different. The pressure/enthalpy chart is used to plot the complete refrigeration cycle as a continuous loop. The selected reference point for measuring the heat content in a refrigerant is -40 degrees Fahrenheit. The pressure/enthalpy chart in figure 3.41, so 3.41, the reference point used for measuring heat content is saturated liquid at -40 degrees Fahrenheit. It shows that the enthalpy, or heat content, in BTUs per pound, along the bottom of the chart, has a value of 0 BTUs per pound when the refrigerant is a saturated liquid at -40 degrees Fahrenheit. The heat content for temperature readings below -40 degrees Fahrenheit saturated liquid are indicated as being negative. As we move from left to right on the chart, the heat content per pound of refrigerant increases. As we move from right to left, the heat content per pound of refrigerant decreases. As you inspect the pressure/enthalpy chart in figure 3.40, you will notice that there is a horseshoe-shaped curve in the center of the chart. This curve is called the saturation curve and contains the same information that is contained on the temperature/pressure chart discussed earlier. The only difference is that the pressure on the pressure-enthalpy chart are expressed in absolute pressures, PSIA, instead of gauge pressures, PSIG. Highlight. Anytime a point lies on or under this curve, the refrigerant is saturated and will have a corresponding temperature and pressure relationship. There are 2 saturation lines on the chart. The saturated liquid line makes up the left boundary of the saturation curve. If while on this line heat is added, the refrigerant will start changing state to a vapor. If heat is removed, the liquid will be subcooled. The saturated vapor line makes up the right boundary of the saturation curve. If while on this line heat is added, the vapor will superheat. If heat is removed, the vapor will start changing state to a liquid. The saturated liquid and vapor lines meet at the top of the saturation curve. This point is called the critical temperature or critical pressure. Above this point, the refrigerant will not condense. It is a vapor regardless of how much pressure is applied. The area between the saturated liquid and saturated vapor lines inside the horseshoe-shaped curve is where the change of state occurs. Whenever a point lies between the saturation lines, the refrigerant is in the partial liquid, partial vapor state. The slanted near vertical lines between the saturation liquid and saturated vapor lines are the constant quality lines and describe the ratio of vapor to liquid in the mixture between the saturation points. There are 9 of these lines under the saturation curve, each of which represents 10%. The saturated liquid line on the left side of the curve represents 0% vapor and 100% liquid, while the saturated vapor line on the right side of the saturation curve represents 100% vapor and 0% liquid. The 9 constant quality lines that are located under the saturation curve are labeled from left to right, 0.1 through 0.9. These figures represent the percentage of quality. Percentage of quality means percentage of vapor. Highlight. This means that if a point falls on the 0.2 constant quality line, it would be 20% vapor and 80% liquid. If the plot is closer to the saturated liquid curve, there is more liquid than vapor. If the plot is closer to the saturated vapor curve, there is more vapor than liquid. For example, let's find a point on the chart at 60 degrees Fahrenheit, horizontal line under the saturation curve, and 45 BTUs per pound along the bottom. Figure 3.42, this is figure 3.42. The quality of saturated R410A at 60 degrees Fahrenheit with a heat content of 45 BTUs per pound is 10% vapor and 90% liquid. This point is underneath the horseshoe-shaped curve and lies on the 0.1 constant quality line. This means that the refrigerant is 90% liquid and 10% vapor. Figure 3.43, next page. Skeletal pressure / enthalpy diagrams. So this top left one, we have pressure PSIA on the y-axis, enthalpy BTUs per pound on the x-axis, saturated liquid line, critical point, saturated vapor line. This is a good one here. Subcooled, saturated, superheated regions. So as you can see on the left, we got subcooled liquid region. Underneath the curve, we have the saturated region, phase change region. On the right, we have the superheated vapor region. I still don't know what superheat and subcool mean. I think it has something to do with pressure. Okay, the next one down, it's just the curve, and it's got the lines of constant quality, which means percent vapor. Percentage constant quality lines. Okay, well, I'm kind of understanding this. Makes me feel smart. Okay, figure 3.43 summarizes in skeletal form the important regions, points, and lines of the pressure / enthalpy diagram. For practical reasons, we will use only a few of these skeletal forms for illustrating the functions of the refrigeration cycle. A refrigeration cycle is plotted in figure 3.44. Flip to the next page. Figure 3.44. A refrigeration cycle plotted on the pressure/enthalpy chart. The system to be plotted is an air conditioning system using R410A. On this chart, 5 important points have been identified. Point A, outlet of the condenser and inlet of the metering device. Point B, outlet of the metering device and inlet of the evaporator. Point C, outlet of the evaporator and the start of the suction line. Point D, end of the suction line and inlet of the compressor. Point E, outlet of the compressor and start of the condenser. The system is operating at 120 degrees Fahrenheit condensing temperature, 417.4 psig or 432.1 psia discharge pressure, and at an evaporating temperature of 40 degrees Fahrenheit, brackets 118.3 psig or 133 psia suction pressure. The cycle plotted has 20 degrees Fahrenheit of subcooling as calculated by the difference between the condenser saturation temperature of 120 degrees Fahrenheit and 100 degrees Fahrenheit condenser. Ooh, cliffhanger. Okay, well, this is a more normal time, 12 minutes. Glad we got through that. It's time for a little sip. See y'all tomorrow.